Okay, so welcome to our machine learning seminar. Today, we'll have a pleasure to have a presentation from Zhang, who is affiliated in the University of New South Wales in Sydney, Australia, but he's now, as far as I understand correctly, he's broadcasting from China.
Yeah.
And the title is visible there. So Han, the visual floor is yours. Please go ahead.
Okay, yeah. So hello everyone. I'm Han and I'm from the University of New South Wales, Australia. Today my topic is artificial neural method based on boundary integral equations. This paper that was my research thesis paper, and I was affiliated with Dr. Elena, and I also got some help from Dr. Cosme and Professor Stephen. So let's and we also submit this paper for publication. Yeah, so let's start. So firstly, I'll do a simple introduction. I know you guys are all experts in this field, so just for warm up. So firstly is about boundary value problem. So in practical engineering, the most of engineering question could be described as a boundary value problem, which is typically a differential equation together with a set of additional constraint boundary conditions. And typically we have three boundary conditions: Dirichlet, Newman, and mixed. For Dirichlet, that we know the boundary value. For Newman, that we know the flux on the boundary. And for mixed condition, we have part of Dirichlet and part of Newman, just like this plot. And yeah, there's also some other boundary conditions, such as the Cauchy boundary condition, but it's it's not part of this research. Yeah, so we just skip it. Here we have a simple example of the boundary value problem, which is a heat conduction problem under a pure Dirichlet condition. That we know the value on each side, and we are trying to approximate the value of the flux inside the whole domain. To solve the boundary value problem in current industrial engineering, the most frequent used method is the finite element method. But for our research, we are more focusing on the boundary element method. Comparing to the finite element method, rather than taking collocation points not only on the boundary but also inside the domain, we are only taking the collocation points on the boundary, which will make it easier to access and do measurements. And if we only work on the boundary, it will lower the question by one dimension, and it will make the question be less complex to solve. Then with the boundary element method, the boundary value problem will be firstly transformed to a boundary integral equation that we could solve with some proper manner. And for this research, we will solve with artificial neural network. Here are some current research about artificial neural network relating to partial differential equations, also boundary element method. Next, AN. Yeah, we all know AN. So in this research, we are using the most basic architecture of the artificial neural network, which is the deep neural network. So for the deep neural network, it's basically a computational graph simulating the biological neural network inside the human brain. Here we have a simple structure of the AN. We have input layer here, output layer here. There's multiple layers between them. Each layer will have multiple neurons. Each neuron will connect to neurons in adjacent layers. Each neuron will have its own weight and bias, and the connection between each neuron could be expressed as this equation. Also, the connection between each layer could be expressed as this equation in a matrix form. So apart from the structure of the artificial neural network, there are two key elements of the artificial neural network. One is loss function. It is basically a estimate telling us how our neural network works, and if we want it is the key term to modify if we want to use the artificial neural network to solve different questions. Apart from that, the optimizer is also an important element. It is essentially a set of mathematical functions that helping us adjust the weights and bias, hence reduce the loss at a certain learning rate. So in current research, the most frequently used optimizer is the SGD and ADAM. They are all derivatives of the gradient descent method, which is a first order method, and it has a general expression of this equation. Also, if we include some second order information, approximation based Newton method or quasi-Newton method could be also considered for optimization. For example, we have the LBFGS algorithm. These both LBF algorithm and the SGD and ADAM has been tested in this research. Next, let's go to some details. Firstly, about boundary integral equation. To illustrate it, let's consider this simple Laplace equation under 2D under a mixed condition. So firstly, to solve it, we need to generate this fundamental solution. It is really well known and has been proven years before. Then with the green theorem, we could have our boundary integral equation as this form. So firstly, the term P denotes the collocation point and term Q denotes the integration points. The term C of P is a term describing the shape geometry at our collocation point. And the kernel Q star is the normal derivative of our fundamental solution. Then I'd like to introduce the isoparametric concept to the boundary element method. So firstly is about nerves. So nerves is also known as non-uniform rational B-splines, which is a mathematical modeling technique using B-splines to describe geometry. It has been massively used in current industrial engineering, industrial design, such as the software that AutoCAD, Beam, Revit, and Rhino. Here's a simple heart shape that I created with 10 control points with the nerves. Here are two models that I created years before with Rhino. Let's go to some detail about nerves. So firstly, the most important element of the nerves is the knot vector. We denote it as psi in this research. So basically, a knot vector is a series of a value that a series of non-decreasing values starts from 0 with a total number of n plus p plus 1, where the n denotes the number of basis functions, also the number of the control points, and the term p denotes the degree of nerves. Here's the general expression of the basic function for different degree. When degree equals 0, it will be as this equation. And for higher degree, it will be like this equation. Then we introduce the nerves, which have the idea, the concept of weights. That different control points will have different weights. Also, maybe let's say influencing degree to the curve. And with the weights, we'll have our basic function for nerves like this equation. And all the points inside the curve could be described with or estimate with this equation. Yeah. In 2012, Dr. Simpson has first introduced the isoparametric concept to the boundary element method, which lead to the isogeometric boundary element method, or IGBM for for abbreviation. And with that method, with IGBM, the boundary integral equation will be like this form, and we will be working on this boundary integral equation. So firstly, it's about the singularity. We may find there's a weakly singularity happening with the U star kernel, and strong singularity happening with the Q star kernel for Laplace equations. So to solve the singularity, we firstly, for weakly singularity, the most common way is to use a tight transformation method, which introduces a new parameter gamma, let's say gamma here, to force the function or force the integration to have value to be equal to 0 at the singular point. And for the strong singularity, there are multiple ways of multiple methods, such as the singularity subtraction technique or Taylor expansion with abandoning the higher order terms. And for our research, we use a regularization method, or maybe known as the constant subtraction technique. So this method is to solve the singularity by remove the singular point. And with this method, the left-hand side of this boundary integral equation will be like this form. After solve the singularity of the boundary integral equation, we will have the boundary integral equation will be like this form. And we will then introduce our artificial neural work here. So yeah, so since for both since for both Dirichlet condition and Newman condition, we will know either the value of left-hand side or right-hand side of the boundary integral equation. For Dirichlet, we will know the value of the left-hand side, and for Newman, you know the right-hand side. So we can let the neural work to approximate the value of the unknown part. And with multiple collocation points and mean square error method, we could define our loss function as this form. Let's go through some benchmark problem as examples. So firstly, let's consider this circle geometry under the heat conduction problem. We define this circle geometry with radius equal to 1 governing with this problem. The loss function will be at this form. You may notice there's a new introduced term here. That is for pure Newman condition. Since for pure Newman condition, the question could not be solved unless a fixed given point on the boundary. So we use this term to force the neural network to have the same value at our given point. Here's the performance. We initially proceeded with pure Dirichlet condition. Here we have the convergence plot of loss and L2 norm against the training iteration. Here's the comparison plot of the result. We then proceeded with pure Newman condition and also mixed condition. For mixed condition, the upper half of circle would be Dirichlet and lower half be Newman. And we could see the result looks quite good. Then let's consider this peanut shape, and we still consider it as a heat conduction problem governing with this question. And one thing shall be noticed that for this question, we've used two neural networks to solve this question for mixed condition. But for the first example, we only use one neural network. Since for the first example is a special case that the temperature and the flux will have the same value at the joint point. But for here, they do not have the same value, and there will lead to a discontinuity. And hence, we use two neural networks to solve it. For mixed condition, we consider it left-hand side to be the Newman condition and right-hand side to be Dirichlet. Here's the performance. We could see there's a jump happening here, which is the joint of the two boundary conditions. Here's the convergence plot and the comparison plot. Overall, there's it could be seen that there's some minor errors happening, but overall it's in an acceptable range, I think. Lastly, we proceeded the training with a quarter annulus. Still consider it as a heat conduction problem, and under mixed condition. Let's consider it as a radiation problem, like the temperature is radiating from the outer edge to the inner edge. And with these governing questions, loss function will remain the same. Here we use 4 neural networks to solve this question, since there's 4 different there's 4 discontinuity with boundary conditions. And with this example, we have gradually increased the number of collocation points and integration points, along with the increasing of the training iterations. And with more and more collocation points and iteration, and with more and more collocation points and integration points, the result looks much more better. Here is the final result after 10,000 training epochs. 10,000 training iterations. In conclusion, we have proved the feasibility of the artificial neural network method for boundary integral equations, and we have admitted that there's some minor disadvantages that since the neural network is indeed continuous, and if we are dealing with some complex shape or some complex curve, which have a little bit more discontinuities, we will have quite a lot of neural network to train, and it will lead to quite long training time. Apart from that, the method looks quite good, and yeah, since for this exam, for our research, we only illustrated the key conduction problem with Laplace equation. The method could be further extended to other fields such as fluid control or theory of elasticity. Also, the further research about higher dimensional, such as 3D or 4D, that include time-dependent problem, will be potential researching topics. And that's all. Thank you.
Thank you, Zhang. So I'm opening the discussion now. So whoever wants to ask a question, just raise your hand and ask question. I can have one in the beginning because I'm not sure if I got it correctly, but I am not sure what's the input to your neural network and what type of neural network do you use? Because I was at some point I was a bit confused.
Yeah, since we use the nerves to describe the geometry, and we input the node, a series of nodes to the neural network, and then let the neural network to solve the let's say this term, which let's say maybe we could say it's a flux or the temperature for us. Because since for pure differential condition, we will only know the temperature and we do not know the flux. So we let the neural network to solve the flux, and we could generate the other hand side of the boundary integral equation, and we could build up our loss function.
Yeah. Okay, so as the inputs, you have the geometry only without the boundary conditions.
We have our as input. We have our nodes. We have our geometry only. We have our geometry together with part of the boundary condition. Like if we have a circle geometry with pure differential condition, the pure differential condition will be used to form the loss function, and what we input is only all the nodes to the neural network.
But the nerves is not only the nodes, right? It's the important part of the description of the nerves is also the weights.
Yeah.
So and you only have the nodes as the input.
Yeah, we use it to approximate this term in the in the boundary integral equation. Sorry, actually this term times this term. Yeah.
I see. And again, in one of the slides, I didn't understand what do you mean by you mentioned that you along the training procedure you are increasing the number of collocation points.
Yeah.
I'm not sure if I understand the training procedure then. Because
so like initially we are proceeding let's go back to the so where's here. So initially we have only how do I say? Yeah, so initially we will have only like 12 collocation points and 12 integration points for how do I describe that? Yeah, so let's say this plot. So we need so for the loss function, we will need a series of integration points to do the integration, and a series of collocation points to form the mean square to proceed the mean square error method. And so we increase the number of the collocation points and the integration points. Yeah, does it make sense?
Well, maybe I still don't understand the let's say the general structure of the problem that you're solving.
Yeah.
You have your integral equation.
Yeah,
and
so
it is a sum over all collocation points and integration points already.
Yeah.
Left hand side and right hand side as well. And
So
left hand side is your and so your input is your left hand side, or what's your input again?
Sorry, like for let me see. So like for let me take an example. So let's say for this circle, let's say we have this pure Dirichlet problem that we know all the temperature on the boundary, and we input our we use the boundary condition together with the boundary integral equation to form the loss function. Then we input our the geometry to the neural network, and let's say since we know all the points, so since we know all the temperature on the geometry, but we do not know any of the flux, and with this boundary integral equation, we could use it to solve the flux. The opposite of the neural network is the flux.
Okay, is the flux based on the geometry.
Yeah.
And you assume that the boundary conditions are fixed. This is not something that is at the input of your neural network.
Yeah.
So again, what does it mean that you are increasing the number of collocation points during the training?
Yeah. So we need to let me see. How do I describe that? So so with each collocation points, we will only form one time of this boundary integral equation. And when we increase the number of the collocation points, it will lead to more boundary integral equations. And with more and more boundary integral equations, the result will be more accurate. And for integration points, it's just to make the integration to be more accurate.
I see.
Yeah.
Okay. Okay. Thanks. And
Thank you.
Let's see if there are any more questions. Okay, it seems that it was clear to everybody, or maybe there will be some further question in the future offline. So Han, thank you very much for your presentation and for your time here.
Thank you. Thank you for you guys.
Thank you everybody for your attention today. And yeah, have a good day.
You too.